Okay, we're going to continue with chapter 7, and we're going to move on to acid-base reactions. Okay. So an acid-base reaction is one in which a hydrogen ion, H+, is transferred from one chemical species to another. An acid is a substance that will dissolve in water to yield hydronium ions, H3O+. And an example is something like hydrochloric acid, HCl. It's a strong acid. So when you put HCl in solution of water, call it aqueous, it reacts with the water to pull the H+ off of the HCl. So as in point number 1, it's a reaction in which the H+ is being transferred from the HCl over to the water. And so you're leaving behind the chloride, and you have the hydronium ion, H3O+. So this is an acid-base reaction. H+ ions are transferred from HCl to the water molecules. So this just shows you a picture, a more visual way to look at that. HCl is a gas, so in order to react, it has to dissolve into the water. And then you can look at how the chloride is being left behind. And now instead of water molecules, you have oxygens with 3 H's on them. So they've changed that structure to make a hydronium and left behind the chloride. And the chloride is negative, so they're showing you the picture to represent how the charges can help be neutralized, which we'll talk about later in the block. So strong acids are where virtually every molecule dissolves in water. And so HCl, in this case, you draw that as a single one-way arrow. All the HCl that you put in is going to react with water to make each of those molecules of HCl now into an H3O+ and a Cl-. Acids that completely react in this fashion we call strong. So I'll always tell you when you're looking at a problem if it's a strong acid or not. These are some formulas for the set of most of the strong acids. So hydrobromic, hydrochloric, hydroiodic, nitric, perchloric, and sulfuric. We'll see with the sulfuric, it's only one of those protons that comes off completely, even though both of them act like acids. So a weak acid, there are far greater number of those. There are tables and tables of weak acids. So there are about 6 strong acids, but far greater number of acids are called weak acids, and they only partially react with water. So a large majority of dissolved molecules remain in their original form, and only a few of them react to form hydronium ions. So this is how you would represent that acetic acid, which is the sour taste in vinegar, is the H3 or CH3CO2H molecule. The proton comes off, it reacts with water to make H3O+, and then you're left behind with that acetic acid with 1 less hydrogen on it, and therefore it would be negative because the hydrogen left as the plus cation. So when you look at this, you don't draw a one-way arrow, you do a two-way arrow that says some of it remains on the reactant side as total molecules of acetic acid, and some of them dissociate to make hydronium and the acetate cation. And in this case, it's actually telling us how much. Only about 1% of those molecules are dissociated. So that double arrow indicates this, that you have some of the reactants and some of the products present. Can be any ratio. In this particular case, it would almost all be reactants. This is also an acid-base reaction. You're needing, though, for the water to pull the proton off of the acetic acid. It doesn't come off all by itself. So these are just some of the molecule or some of the things that you interact with. Citrus and wine, they have acetic acid and citric acid in them. A lot of things that you eat and drink are acidic. So a base is a substance that will dissolve in water to yield hydroxide ions, which are OH-. The most common bases are ionic compounds composed of alkali or alkali earth cations combined with the hydroxide. So that would be sodium hydroxide, potassium hydroxide. Notice calcium hydroxide, because it's a group 2, calcium would have a 2+, and hydroxide only has a -1. So you're going to get 2 hydroxides for every 1 calcium hydroxide. Same thing for the barium hydroxide. You get 2 hydroxides for every 1 barium hydroxide that dissolves. So these bases, along with other hydroxides, completely dissociated in water and are considered strong bases. So you would write it, it's essentially a solubility reaction, but it's a one-way arrow. Sodium hydroxide solid dissolves when you put it in water to make Na+ and OH-. So the dissociation process is essentially complete with sodium hydroxide. So that means all of the sodium hydroxide you put into water will be pulled apart to form Na+ cations and OH- anions. This process is a dissociation, not an acid-base reaction. So just dissolving this is not an acid-base reaction. Other weak bases, some compounds produce the hydroxide ions when they're dissolved by chemically reacting with the water molecules. So in all cases, these compounds react only partially and are classified as weak bases. So something like ammonia, which is in your cleaning solutions at home, oftentimes NH3, and that 3 should be a subscript. If you put that in water, you don't have an OH- in that molecule, but when you put it into water, it reacts with water. So it's going to pull off a proton from the water, which leaves behind OH-. So it's a base because it created OH- through a reaction with water. This is an acid-base reaction because a proton is transferred from a water molecule to the ammonia molecule. So in this case, the water is the acid, the ammonia is the base. And this is just a picture of the fact that we use ammonia on our crops as a fertilizer. It's a source of a lot of nitrogen pollution. So when we talk about an acid-base neutralization reaction, it's a specific type of acid-base reaction in which the reactants are acids and bases, and the products are often a salt and water, and neither reactant is the water itself. So for example, you take magnesium hydroxide as a solid, you put it into a solution that has hydrochloric acid in it, and a reaction will take place where the OH- that came off of the magnesium hydroxide can react with the H+ that came off of the HCl, and that will be neutralized and make water. And what's left behind are the cation Mg2+ and Cl-. So that magnesium chloride is called a salt. So you get salt in water. This is just an example of how when you put citric acid in lemons onto fish, what kind of reaction takes place. Okay, so now we're going to go on to another type of reaction, oxidation reduction reactions. So some redox reactions involve the transfer of electrons between reactant species to yield ionic products. It's helpful to split the overall reaction into individual equations called half reactions. So when sodium solid reacts with chlorine gas in this overall reaction, you can make sodium chloride solid. So we'll notice that if we split those, what's actually happening is the sodium solid, which is neutral, it has all of its electrons, is giving up 2 electrons to form Na+ cations. And then the chlorine needs electrons to become chloride, Cl-. So the top reaction we will call an oxidation, and the bottom one a reduction here in a second. So the sodium atoms lose electrons, the chlorine atoms gain electrons. Loss of electrons is called oxidation. Gain of electrons is called reduction. So that means that sodium is losing electrons, so it's oxidized, and chlorine is picking up electrons, so it's reduced. So this sometimes gets confusing, but if sodium is being oxidized, it's a reducing agent. It's an agent that can force something else to be reduced, something else to pick up electrons, because it's losing electrons. So whatever is oxidized is the reducing agent, and whatever is reduced is the oxidizing agent. So some redox reactions do not involve the transfer of electrons. So when we look at this, the product of this reaction is a covalent compound, so transfer of electrons in the explicit sense is not involved, but the oxidation numbers change. So we'll see in a second, there are a set of rules that will tell us that if you have elements by themselves, such as H2 and Cl2, those will have oxidation number of 0. And on the product side, when you have H in a compound with Cl minus, the H is going to be positive 1, and that means that the chlorine will be -1. So the oxidation number of an element in its elemental substance is 0. That's what I just said. The oxidation number of a monatomic ion is equal to the ion's charge. So oxidation numbers for common nonmetals are usually assigned as following: that hydrogen likes to be +1. It's -1 when it combines with a metal. Oxygen is almost always -2. Sometimes it's -1 if you call it a peroxide. Very, very rarely it's -1/2 if you call it a superoxide. And positive values when combined with fluorine. So you have to be told those three, the sometimes, very rarely, and when it's positive. In general, oxygen is -2. Halogens are -1 for fluorine always, -1 for other halogens, except when combined with oxygen or other halogens. So we'll look at some of those cases. So the sum of the oxidation numbers for all atoms in a molecule or polyatomic ion have to equal the charge on that molecule or the polyatomic ion. So if we follow the guidelines in this section, we can assign oxidation numbers to the elements in the following species. So according to guideline number 1, if we want to know the oxidation numbers of hydrogen and sulfur in this compound, hydrogen is +1 because sulfur is not a metal. And so that means sulfur has to be -2, because 2 times +1 for those 2 hydrogen atoms has to add up with what other sulfur's oxidation number is to give you a 0. So the oxidation number is essentially a theoretical charge. So H2S is a covalently bonded molecule, but it's a hypothetical charge that would be on each of those elements if it was ionic. So we want to look at SO3 minus, which is sulfite. We know that oxygen is -2 from our second rule. And therefore, if the whole thing has to add up to 2-, we have 3 oxygens, each at -2. And then we have to figure out what sulfur is based on sulfur's charge has to add to that to give a -2. So that means sulfur in this polyatomic anion has an oxidation number of +4. So we want to solve or give the oxidation numbers of each of these species. So it's an ionic compound, so it's convenient to assign oxidation numbers for the cation and anion separately. So all sodiums, if you go back to your solubility table, all sodium salts are soluble. So what you'll have actually is 2 Na+ cations and 1 SO4 2- sulfate anion. So first we'll start out by saying that the sodium is +1, and we have 2 of those. So that means we have 2 times +1 contribution from the sodium. And so if we assign the oxidation numbers for oxygen, we'll figure out what it is for sulfur. So once you assign the oxidation number for sodium, now we can look at the anion separately. So we had 2 Na+ cations combined with 1 SO4 2- anion. So the charge on that whole SO4 has to add up to 2-. And so if you have 4 oxygens each at -2, that's -8. So sulfur has to add up with that to give -2. So the sulfur oxidation number has to be +6. Using the oxidation number concept, an all-inclusive definition of a redox reaction has been established. Oxidation reduction reactions are those in which one or more element involves undergoes a change in oxidation number. So oxidation equals an increase in oxidation number, reduction equals a decrease. So if you think about it, if oxidation is loss of electrons and electrons have a negative charge, then your oxidation number is going to go up if you've been oxidized, and it's going to go down if you're reduced, because when you're undergoing reduction, you're gaining electrons which have negative charge. Okay, so here are just some examples of some redox reactions. So this is a fuel and an oxidant, something to react it with. And that is an example of that picture they showed of that rocket that had a solid fuel mixture. So this shows you that you'd have to mix the solid aluminum and the ammonium perchlorate in a 10:6 ratio in order to get them in equal quantities so that all of it could react. Here's another type of redox reaction, and I'm not going to ask you to understand the single displacement replacement, but all it's really showing you is that the copper replaces the silver with the nitrate, and that the silver goes on to become a neutral metal in this particular reaction. And this is one that I'll do in class for you. And that is a picture of the reaction as I will do it in class, exactly the same. So you really want to be able to balance these reactions. If you're thinking about, for example, batteries or fuel cells, which are very, very, very important machines when you're thinking about renewable energy, how do you store the energy, usually in a battery or some sort of chemical system? You want to be able to balance these. And so we're going to balance them using something called the half reaction method. So redox reactions that take place in aqueous solution often involve water, hydronium ions, and hydroxide. Although these species are not oxidized or reduced, they do participate in the chemical change in other ways. These reactions are difficult to balance by inspection, and a useful approach to balance these is called the half reaction method. And this probably, so far in the class, more than anything, you have to practice these on your own in order to get it down. Just watching me do them never seems to be quite enough. So here are the steps, and I would strongly recommend that you put these on your note card. So first you want to do is write the two individual half reactions, the oxidation and the reduction. Balance for all elements except oxygen and hydrogen. Balance oxygen atoms by adding water molecules. Balance hydrogen atoms by adding H+ ions, and then balance charge by adding electrons. So we'll talk through this process. Then if necessary, you're going to multiply each half reaction by the smallest possible integers to yield an equal number of electrons. Add the balanced half reactions and simplify. And for reactions occurring in basic solutions, so when we use this set of rules, this said that we have what our reactants are and our products, but then we also have in a beaker. So if the reaction's taking place in an aqueous acid solution, we also have water and H+. But if it's taking place in a basic solution, then we have to think, well, you can't have H+. So we'll look at how you're going to get rid of the H+ by neutralizing it with OH-. And your final step is always to check to see that the number of atoms and total charge are balanced on both sides. That's an official step. Don't skip number 9. You'll always be able to know if you did the balancing correctly. So we're going to look at this reaction. Sorry. Between, I think that's dichromate and the iron 2 cation forming chromium 3 and iron 3. So the first thing we know is step 1, write the two half reactions. So iron has to go to iron, chromium has to go to chromium. And now we're going to balance for all elements except oxygen and hydrogen. So the first one's already balanced, 1 iron, 1 iron. But the dichromate, you have 2 chromium atoms in each of those anions. So you're going to have to put a 2 out front of the Cr3+. And now we want to go on to step 3, balance for oxygen by adding water molecules. first half reaction doesn't have any oxygen, but in the second one, on the left-hand side, you have 7 oxygen atoms. So you have to add 7 water molecules to the right-hand side to get the oxygens balanced. And now we have to balance the hydrogens. So when we look back here, you can see on the left-hand side for the dichromate, you have no hydrogens, but on the product side, you have 7 times 2, so you have 7 hydrogens. That means that you have to add 14 H plus to the reactant side in order to get all the hydrogen atoms balanced. Now we're going to balance the charge. So the only thing we can balance the charge with is electrons, because if we balanced it with any of the elements or ions, we'd be changing that balance. So in the top one, we have iron 2 plus going to iron 3 plus. So in order to get the charge on both sides to be equal, it's 2 plus on the left-hand side, it's 3 plus on the product side. So if you add 1 negative electron, that will cancel one of those positive charges, and now both sides will be balanced. And if you look at the second half reaction, on the product side, you have water molecules that are neutral, so those don't contribute once they're there, but you have 2 chromium 3 plus cations, so that means you have on the product side 6 plus charge overall. So we need to take the dichromate, which is -2, and 14 plus 1s. So we have plus 14, and we need to add to that 6 electrons so that we have plus 6 left on each side. So once you add those 6 electrons and add that all up, you will see that you had 2 minus plus 14 gives you plus 12, plus 6 minus cancels 6 of those, and so you're left with plus 6. So now we have to look at those two, and we have to say to ourselves, we need to have enough iron to give as many electrons as the dichromate needs. So here, if it's just 1 to 1, it would say iron is giving up 1 electron in an oxidation reaction, but the dichromate wants to pick up 6. So in order for that reaction to take place, you have to have 6 times as much iron so that you get 6 electrons produced in the oxidation so that you can have an equal amount in the reduction half reaction. So once we do that, now the electrons are equal, and now we're ready to add them together and then cancel everything that's redundant. So once we add them together, 6 electrons, 6 electrons, the electrons always have to cancel. You can't use more or create more from the oxidation or reduction. And then when you look at the other species, I don't think there are any spectators. Nope. So everything else remains as is. Okay, so now we want to do the final check of the charge and atom balance. So we have 6 atoms of hydrogen on the reactant, 6 on the product, chromium, 2 reactant, 2 products, oxygen, 7 reactant, 7 products, hydrogen, 14, 14. And the overall charge on each side is plus 24. So that reaction is balanced. Both the charge is the same on each side, and you've accounted for each element on each side. Okay. I think this is where I decided we'd take another break because reaction stoichiometry will use these reactions, but it's a different idea. So I think it's a good time to take a break rather than to get started into it. So we will end up with 3 lectures for